Bueno, pues buenas tardes a todos y muchas.
Good evening, everyone, and thank you for being here with us in Espacio Telefónica, and alongside Mr. Foster, Norman Foster's exhibition upstairs. I hope you have already been there, and we have another one, and we are very grateful for sponsoring this forum on robotics. Many of the participants are here with us today, and today is a key moment in this forum because we have Matthias Kohler who will speak for us. We know him very well. We've published him here in Spain, and he was also at the Foster Foundation launching in the Teatro Real Opera House, and he, well, we were amazed by his presentation, and now you're going to speak even for a longer time.
Very excited with the prospect of listening to Matthias Kohler. And y para finalizar, o para...
And to finish with, or to go along with this, we have Amelie Klein from the Vitra Museum, and although she lives in Vienna, she travels often to Basel to take care of a classical museum. And it's a great museum that doesn't only have great archives from the hemos and others. She has participated in excellent exhibitions, watched closely very often by Amelie Klein. She will speak with him on robotics. And I just have to thank you for being here. And I would like to thank Norman for being here as well, because at the end of the day he's the final reason why we are here, and also the Gavillas studio. And also please give it up for Matthias Kohler.
It's a pleasure to be here for the second time in Madrid, invited by the foundation, by Elena and Sir Norman Foster. So it's a great pleasure to be here, and I would also like to thank in English the Rolex Institute for enabling the first educational workshop at the Norman Foster Foundation, which we're conducting with robots here in Madrid. So it's a great opportunity. Now I would like, is it fine, the sound? Yes? Good? Okay. Now I would like to present you a bit, get a bit out of the picture, present you our works, and also I would like to go a little bit back in time, as you will see. As you all know, the world is rapidly changing. We have rapid advances in technologies, such as the digitalization and robotics, and society is confronted with a lot of challenges nowadays. And what is maybe a bit less known, but is also discussed widely, is that the way that we produce is also changing. So the entire manufacturing industries is going through a tremendous change. 3D printing, as one example, robotic fabrication, and so on, is on its way. So the way that we manufacture our physical world around us, that's about to change as well. And the question that I would like to ask is the way that we're actually going to build buildings also change? And the answer that I'm going to give you is very simple. It's yes, it's going to change. And if you Google, for example, robotic fabrication in architecture, you get a lot of images like those, and you start to realize that actually on a global scale, in many architecture universities around the globe, architects are using robots to produce architecture of the future, or to study how architecture of the future might be produced using robots. And also at the Norman Foster Foundation, this is currently a topic which shows the relevance of these changes. And I think in the midterm you're going to see how we move towards what I would refer to as a digital building culture in architecture. And you know, the building culture was always very important in architecture. The way that you construct a building is the way that you will also design the building. Or in other words, you will design the building for a way to be built. And each time the way that we build, change the way that we that we build a building, we also change the way that we designed these buildings. And I think we're in the midst of such a transformation. Here you see a picture from the Swiss National Center of Competence on Digital Fabrication, just a lab picture indicating the spirit of research into new production methods, which will entail new design methods. Good, so now we go a bit back in history. This was a bit younger here, all still in the picture. This is Fabio Gramazio to my right-hand side, and we started as an architecture office just in Switzerland in the year 2000. And one of the earliest exploratory projects that we've been working on was called M-Table. So this project is by now 15 years old. That's 5 years before the first iPhone, and this was the first programmable phone that was available on the market. At that time that was by Nokia, and we used this phone and wrote a little software, today you would call it app, that enabled you to design a table on that phone. You could push with your button, you could deform a surface with your thumb, and you could choose the dimensions of the table and choose the color, and once you're done you send this very small code to a server, and this code tells you where you pushed with the button, how much you pushed there, and so how much force you exerted on this virtual model, what color it has, what the name that made these changes. This is the RAL code, this is the dimension, length, width, height, etc. And so these few numbers got transmitted, and that's all you need to transmit the form of these very personal, intimate actions that you've done with your thumb. And then on a server it recreated this high-resolution surface. So from this low-resolution display to this high-resolution surface, and this is then the basis for a milling action. So what you've done with your thumb is what then this computer-driven mill takes off this tabletop. And the tabletop is actually the underside of the table in this design. So the table looks like this. It's a table with holes. Yes, there is some irony here, but it's a kind of a negative decoration. It has features this very thin, very razor-sharp edges, which kind of are an indication that there is something happening on the underside of this table. If you sit at this table, there is a tendency that you want to touch and reach underneath. You want to understand what's happening underneath this table, and indeed there is this pressure surface underneath. We built a number of these tables. This one is at the Vitra collection. And if the table gets too low, this sculpted surface goes to the upper side, because we consider you cannot see or feel the underside anymore. Now, this was an early design experiment, and I think the most important take from this design was that indeed, as architects, as designers, we could design something which was not defined by form, which classically is the domain of the architect, but is actually more a design system. And if you look at these tables, all these tables, you sense that they belong to a family. They're part of one design. They have an authorship, despite the fact that multiple users or customers can actually decide where they put their holes and how they're going to use this table, how wide this table is. So this shifts the premise from form into the design of processes, and that's something which we're very interested in, and I think architects, designers don't lose authorship through that change. That's what I want to indicate here. We've done other projects where we designed really also dynamic structures, such as the Christmas lighting at the Bahnhofstrasse in Zurich. That's the most prestigious shopping street in Zurich. It's our longest work. It's 1.1 kilometer long, so I think we will not ever build anything longer than this. It was up for 5 years, and here it was not only about this design of this glass fiber filament wound the tube and the suspension in this airspace, but it was also about the design of the behavior of the lights over time. So here this kind of temporal dimension or the procedural dimension of how something can change was part of the design agency. Unfortunately, this project caused a bit of a revolt in Zurich. Zurich was not prepared for the modernism of this work, so in effect it was taken down after one famous Swiss bank sponsoring money to get rid of this one and go back to a more traditional Christmas lighting. But it was up for 5 years. So we've also done houses. Here you see a house which we've built, which is kind of wheeled in wooden slats, and these slats, they thin out in front of the window, and the window bands actually move all around this house. And so what from outside looks like quite a closed or somewhat hidden facade is from the inside turns into a very open building. You're well connected with the outside, and these slats kind of frame the outside in a very particular way, and you sense that this thinning out of the slats is actually opening your viewing angle to nature. And at the same time, the reason why these slats are here is that's the only way that we could build such a house in this zone, because the building regulation only permit you windows like this in size and format. So we could kind of use, let's say, different expressions of architecture to also deal in a creative way with certain building laws. We've been working on projects like this. Here now the research starts to come in. This is a facade, for example, which is robotically assembled. Here we use the fact that if we use robots and we glue bricks together, we can build brick structures which you could not usually build. Here you have basically tensile forces in this vertical diagrid structure, twisting like this. I'm not going to go into the details of this project. This is a collaboration which we did for the Federal Court of Switzerland in Bellinzona. This is more, let's say, interior work. Another project with bricks. And here I think it starts to become interesting, because you see these bricks, you get a sense that you have a depth of the material which is present, and at the same time you also have an embedding of more information in this wall. And I'm going to come to that topic later on. In this case, this is about the acoustic performance of this space. So the way that these bricks are arranged is not only for a visual appearance, but it also creates a particular acoustic comfort in this room by diffusing and reflecting sound waves in particular ways. Now the biggest work that we've done in the architecture office is this building. Now this is a strange building if you look at it. It has virtually no facade. It consists of these cantilevering platforms, and it's actually a research lab. But classically, if you think of a research lab, you think of a containment, and then there is lab work being done inside. This lab is turned inside out. So the lab areas are actually these outside cantilevering surfaces onto which you can build building modules where you have people living in the future. So it's like a plug-in architecture. And the client for this building is the Swiss Material Science Institute, EMPA, and they want to use this as a living lab where you build guest houses for students on top of this using new technologies, and bring together different research groups from all around the world, industrial stakeholders, different companies that want to research new materials or test them out in vivo, and then inhabitants which use this platform. So this is the concept again. This building provides all the infrastructure. It's actually quite complex in its build-up, so I'm just going to give you a kind of a visual walkthrough that you get an impression of this building. So let's say the classical architecture is in the inside of the building, and the outside is transformable. So this is an impression just, let's say, from the architectural practice, but what I want to draw your attention on is with the project that I started. It's an exploratory project on how to design a table on your mobile phone. So designing a process, and the final project, which is a platform for something that actually constantly changes. And you see a bit our motivation to work actually with processes that can be open-ended, or to actually design processes. And that's really a passion that we have. And I take this as a step to the research, which we've been conducting at ETH Zurich since 2005. So our chair is called Architecture and Digital Fabrication, and we started working with robots at the time. Why did we choose the robot in the first place? Well, basically we said, in order to connect the digital with the building practice, we need some tangible connection between the two. And at the time when we were thinking about that, well, the only possibility to connect these two was through using CNC milling processes or laser cutting, certain techniques which were available, which you could use for construction. But there was no tool to actually build architecture, literally additively build up architecture. And you know, if you look at architecture, it's always assembled from different parts, right? Joined somehow, brought together, and ideally brought in a nice synergy, and expressing the way that these constructions come together. And so we thought, okay, we need to start actually assembling. So how do we do that? And that's how we reverted to the robot. So the robot at the first place was not a vision in that sense, it was really the tool to connect the digital world and the physical world of building additively. And the nice feature of the robot is that it's so generic. So if you buy a robot arm, it comes basically without a hand, just an arm that can move in space. Now this is very practical, but what's conceptually very interesting, that you as an architect or designer, you need to think what the robot actually does. So what is this physical action? And actually now in the workshop we're doing a very fun project. We're actually shooting clay, just to give you a bit of a fantasy on what you can do. But there's many possibilities that you can do with the robot. So this is conceptually very interesting. We can think about these options, and we can do additive fabrication with it. Now, in our research, we bring together three domains: the domain of computation, the domain of materials, and fabrication. And we formed a hypothesis that the materiality of architecture is going to change towards the digital materiality. Now, this means that material, as we currently know it, starts to become informed by digital processes. So digital processes, algorithmic processes, and physical processes of building, they start to overlap. There are going to be synergies between those processes, and this will express itself in architectural terms. So if you look at the picture, is this a concrete wall? Yes. But at the same time, you've not seen a concrete wall like this. So what kind of materiality is this now? It leads us to a rethinking of construction, because if you build by hand, or with classical industrial tools, or with a robot, it leads to new construction techniques. There are things which are very easy for a robot, and things which are very difficult for a robot to do, and the same for the human, and that naturally leads to new construction forms that will disrupt industry, construction industry, and the constructive processes. And this is what I was hinting at with the M-Table project. It enables the architects and the designers to design processes instead of static forms. For me as an architect, it's always very impressive to see that through this acceptance of digital technology, we don't get a material, let's say an abstract materialization of architecture, but rather we actually, the kind of material substance and sensuality is being enriched, enhanced. So the expressivity of the materials that are inherent in the building processes is highlighted. And I think this could become a very important feature of future architecture, That means we're maybe less alienated to certain architecture, but we have also different level of details which we humans usually enjoy to see, touch, etc. And I just inserted this slide actually this morning. I think it will also lead to new modes of collaboration. So the roles of the different stakeholders is going to change in, let's say, the architectural design process, also in the execution process, also in the planning process. We just heard the legal, we just had a discussion about the legal processes and so on. So many of these processes are going to change, and also the relation between the machine and the human, and the question who is controlling whom. That's a picture we shot about 12 years ago with our technician sitting on the robot and opening the question, well, who is actually in control? That question, I think, is more actual than ever. Good. So I'll show you a bit what you can do with the robot in architecture. And let me first start with a robot that is classically doing prefabrication in a, let's say, in a factory environment. It's in our research lab in this case, but you can imagine a construction company that uses a robot for prefabrication. We had the chance to design this facade. This is a 400 square meter facade for a winery in Switzerland. You see these over-dimensional grapes. It's like a basket filled with these large grapes. And this is how this facade was being produced. So here you see the robot picking up. Maybe we can have a little bit of sound. Yeah, just that you get the sense of the industrial. So the robot picks up a brick and he glues exactly the locations where the brick is going to touch the lower bricks, and each of these bricks is individually rotated up to 17 degrees in one or the other direction. And so it's only the rotation of the bricks that actually gives you this impression of these oversized grapes on this facade. So it's really just a play of light that creates this depth. And what we like about this, it's less about the overall image, but if you go close, you also sense that each of these bricks is somewhat animated. You know, you sense the material very well if you look at this facade. So it's not just an image, it's literally also the brick being informed. And this double presence of the material and also other information which can be embedded in it, I think that's a very nice topic for architecture. Here's the inside of this winery. Here we had to be very careful to bring these bricks close together so that in the counter light you actually close the gap between the brick almost, so that it's readable. If you would move the bricks a little bit apart, or 3-4 centimeters, and you rotate, you would not see anything in the counter light. I think that's an indication, even if we work digitally, I think the architect still needs a very careful eye to see what happens in the physical. So it's all about synergies. But then you can also take a robot and actually bring it outside. And we had the chance to go to the Biennale in Venice, and here we brought the robot in the shipping container to the site. This was in front of the Swiss Pavilion in 2008, and there the robot prefabricated on site these elements. The elements were about 4.5 meters long, you can see it here, and they had this special form. Now, this was the installation in the pavilion. It's a 100-meter long wall, and the installation is called structural oscillations because wherever this wall was relatively flat, the wall started to oscillate, and wherever the wall was curved, it just stayed curved, just straight up. Now, why did it do that? Well, this was a way to actually have all these individual wall elements standing on by themselves. So you didn't need any further structural support, you didn't need any anchoring in the floor. Basically, it's like a sheet of paper that you fold a bit until it stands. So we embedded the kind of structural logic into this wall, and through that made a very simple constructive system to build this wall. And now you can see these qualities that this wall has. It's has a very textile appearance. It's very lean in material use. You see how thin this is and how elegantly this winds through the space. But you can also see that we did not design the actual shape of these oscillations. We designed the logic, the rules, the algorithm, you could say, on how this forms. And this is a bit the shift that we currently see and the excitement that we have also to design in new ways. Now you can also take a robot onto a building site. This is a lab test where we use the robot to actually build between two walls, these colored walls, and then the location of the bricks is determined dynamically at the moment where the robot comes in, scans the space, and then he builds the structure in between the walls that the robot found. And here we see the robot building this wall. And now you can think, well, basically it means, in this case, the architect would need to design the rules for such a robot so that whenever he finds walls where he needs to build in between, the architect would need to say, well, what do you do then, depending on how these walls stand? What would be the design rules? How can I act? And so you would need to think about how you transport your brains, your intuition, to this robot, basically, and giving him instructions, giving him behavior to act in the sense of the design. I mean, these are just thought loops to think about how the role of design might shift in the future. But sorry quickly if I go back quickly, but this also enables you to not have super precise construction. So you can build a super precise wall in between, for example, a raw construction which is off by 5 centimeters. I'm not saying this is a goal for future construction, but it also kind of relaxes many constraints. But maybe there are completely other machines, so why not building with flying drones? So this is an early experiment we did. So that's a good try.
Ja, ist gut.
That's how we work in research most of the time. So through that we actually found out maybe it's not the best to actually work with these stiff elements which require, you know, absolute precision at the end, and to fly this together with quadcopters. Maybe in the future we can do this, but at the current state we thought this is less promising. Let's change the material. Let's take a material system where we can really use what quadcopters are really good at, and that's actually flying collaboratively and flying through structures. Structures like this scaffold where it attaches to just by looping around, or the structures that the quadcopters themselves build, so weave in space. And that's a collaboration with the roboticist groups of Professor Raffaele D'Andrea at ETH Zurich. He's one of the most acclaimed roboticists for drones. And what these quadcopters are doing here, they're kind of weaving a bridge in a research setting, and then the researchers that built this bridge will walk over it. You're going to see it at the end of this video. And the question was, can we build that only by winding with quadcopters, so no human intervention and also no real knot which is tied somewhere. It's really just winding around with these basic flying vehicles. Maybe one indication for the architects of you, it's not so easy to design this structure, because if you draw a static plan of how that looks, the robots don't know where to fly and in what sequence to fly, right? Also, they don't know about the different deflection states of the rope at a given time. So we needed also to kind of work with the simulation software to actually sequence these entire steps and find a way to simulate this. And here you see the successful passing. So this worked, and 2 people got a PhD here. Good. So a bit earlier than this project, we did an installation also with flying quadcopters with the same professor. With this installation, there was a 6-meter high tower for the FRAC in Orléans, and this tower was autonomously built by 4 quadcopters which changed shifts. So some of them sometimes went to charging while the others continued working, and so on. So no human ever touched this vertical structure. And this is also, we took this as a starting point also for a fictional project. So we said, can we think of this structure as a model for a city? And we co-developed a project for a city and a project for robotic assembly. What you see here is actually the city, so it's a 600-meter high tower. It's a city for 30,000 inhabitants, and it's a city as an object. The idea is that it's fully self-sustainable in ecological terms, so you have energy generation in it, etc. And that's on the one hand side. On the other hand side, you could also take down the city if you don't need it anymore. So the idea is, well, you build it up, but you could also build it back. So you don't just grow city, let's say, carpet over city carpet, but you really contain it in an object and you build it back. That's the kind of conceptual model. It had these double-story park rings. This is 10 meter high. The length of such a ring is 1 kilometer, so you can walk around in this structure. It's fully pedestrian. There's no car in it, of course, but you can also go to the outside because the city is, because the city is located in Meuse. That's a region in France where you have the lowest population density. But Meuse has one thing, it has a TGV station, so the fast train in France, and this TGV station is just 1 hour away from Paris. So you get out of the city, you can live here, you can get into Paris whenever you want. This was kind of the proposal. Good, and this is how this structure got built. This, and here you see how almost from a magic hand this material is just built up. And the next project I brought as a reference to what we currently do also in the studio is called remote material deposition. It's just taking this topic. So we've seen how we take a robot from the factory out, possibly other robots, but maybe there's completely other ideas, and this is one of them. Why don't we just shoot material to where we want it to have? So instead of moving robots with materials, maybe we just bring the material remotely. That was a bit of a crazy idea, but we tried it out, and it actually works. So here there was the first test. So you have this robot portioning a little sample of clay and just shooting it off. You see the structure, yeah, semi-architectural at the given state, but still, I mean, with the students we arrived to build up some structures, or even some wall-like aggregations, and what we particularly liked is the expression of this kind of impact forces and the deformation of these projectiles. So I thought that's interesting, but could we really do it at a larger scale? We were a bit skeptical, could we have the precision, and we tested it. So this was the raw material, so it's basically just earth, clay-like substance, dried, then mixed with water. This was the space, and that's the shooting setup. I'm going to go a bit faster because I see the clock. We extruded clay projectiles, made sure that they all have the same weight, and then we put this on this small cannon, which is directed by a robot. So we shoot it off from this little gallery up to a distance of 10 meters away. We always scan what we produce, so that we know where to shoot next. And here you see one of these clay lumps landing. You see another one. See a larger view. And you see that we actually get surprisingly precise kind of 3D print, if I may say so, with clay from distance. So we use a ballistic principle not for warfare, but really for civilian use. And these structures at some points were very, very slender, so maybe 10, 12 centimeters slender. The highest point I think was 2 meters 30, which we reached in this week. And I mean, it's very prototypical, it's not architecture yet, but you sense maybe there is completely other ways of building which we have not yet thought about. And that's why I wanted to show you this project and how robots could also have a bit more a peripheral role. Here you are sitting at the landing point of a projectile, and you watch one projectile coming. Good. Okay. And now just a quick video of an installation which we did, which shows that just to open the brain a little bit, what we might be able to do in the future. Here is this little particle, which you can see here, this white dot, which is floating 3 centimeters in front of a robot in the air, held by acoustic waves. So if you don't think of space as just void, but think of all the material that's actually here, maybe we can start to interpret it also completely differently in the future. Good. So now you think, well, this is going crazy, right? And it's going smaller and smaller, and you have particles, etc. Where is architecture? So now I would like to quickly show you that we can really do architecture with it. So just to make a counterpoint. We recently moved into our new institute building, and this is it. This was collaboratively designed by 5 people from our institute, and our chair had the possibility to design the roof of this building and the laboratory in this building. So this roof, which you see here, is built from 50,000 slats of timber and assembled robotically. And again, you see it looks a bit like a textile. You sense that there is many parts, but these parts somehow take form, they adapt to certain conditions, they retract, they stretch, and that's very much what the algorithm in this case does. It adapts to different requirements which we have from the building side, and it gets very loose in planning, loose in the sense that it has this malleability as a structure. So it has an optimized structural depth, this roof. It's built in these individual beam elements, 196 of them. Here you see the layout of these individual slats. But what's most important is that it embeds all the different subsystems that the building needs into this roof structure. So you see here these different systems, and now if you combine this with the plan that you've seen, you get a sense on how it adapts to every part. And whenever you change something, so if, for example, you say, well, actually, through the tendering process, we got another manufacturer of the roof light, well, you change the roof light proportions, and this entire roof adapts to it. And that's another advantage of these new design processes, that you actually stay flexible until a very late stage in planning. And what usually causes huge turbulences if you change planning at the later stage, here becomes very easy. If, as an architect, you think ahead what could change later on in the process, you can build it in, actually. This is how such a model looks. So the raw model in the front, and if you render all the parts in it, then it becomes the end model. But this model is not drawn, it's programmed. And to indicate you why programming is needed, I show you this detail on how these slats connect. There's a number of nails here, I think it's 500,000 or so in this roof, which connect these different slats. And it's so complex to bring in these nails and make sure that you have enough structural, you fulfill the structural requirements. At the same time, you don't hit another nail in the next layer. It's really only algorithmically and with the computer that you can do this. You don't want to do this by hand. So this is how it looks like. And this is how the roof is produced. It's the Swiss manufacturer who specifically bought a machine to build this project, but is now able to do all kinds of projects with digital fabrication. So this robot basically takes a slat, cuts the different end angles, then lays them, does this nailing pattern that you've seen before, then changes its aggregate, and does some end cutting, some trimming. And what you really get is something, again, like a 3D printed beam, but here it's not printed from dust and binder or fused together metals or so. It's literally from material as you get it from nature and connection. So it's very classical in that sense, using classical material systems and connection systems. At the same time, it's a fully digital additive construction process. And it's quite economical, and like this we could realize this building. And I can say that we all really like to live and work in this building, so we're the users also, and some other people, and most reactions are really very, very positive. Below what you've just seen, this space, is our new robotic fabrication laboratory. This is how it looks. The floor is empty. The robots just come from the ceiling. It's basically a replacement of what used to be the crane in the hall. And now whenever you need robots or digital control, you just call them. They basically come down and assist you with building amazing structures like these, here designed by Stefana, who's sitting in the audience. Good. Another project leads me to a research initiative which we had the chance to initiate in Switzerland. It's called the National Center of Competence on Digital Fabrication, and it's really grown into an interdisciplinary network of about 70 researchers involving about 15 professorships from ETH Zurich, EPFL, and some of universities of applied sciences. And what we tried to do as a final project of the first 4 years of this program, and this is a 12 years program to really push the development of these technologies in Switzerland, is to say, could we not build a house together at the end? A fully inhabitable, structurally sound house, using all the research technologies. And so actually, the people that you see here are the ones that are all engaged in this house. So almost half of this entire research network is somewhat working on this project. So I'm really talking on behalf of all of these people here, and there are 8 other professorships involved in this project. So now here we reconnect to where we were before, because a really good area to build this house is the Nest building, which you've seen before, and we got a parcel on it, and here you see the program of that house. It has basically a very open ground floor plan with organized around this S-shaped wall, and then it has 4 living units for guest researchers in a quite dense two upper floors. So it's a 3-story unit. This is the parcel that we got. This is roughly how it will look, but I'm not so interested in renderings. It might probably also change. We're really interested in the way that we build and design this. And these are the different research projects that go into this building. What's really new in this building is that it's fully inhabited. It needs to comply to all codes in Switzerland, so be it thermal insulation, fire regulations, etc. And all the structural parts of this building are built by new digital fabrication technologies. So we bring digital fabrication from, let's say, something which has a tendency to be ornamental to something really structural. That's the significant step, even though the building itself is quite a small building. So I'm going to walk you through quickly from below to top, just to give you a first impression. This is currently ongoing, so I also will not go into details. So the first project is really this S-shaped wall, which is built by a mobile robot. This wall has been designed in a way that it can take the forces of, or it can carry the 2 stories on top and take all the forces, also the wind forces, lateral forces of the building. It's being built by a robot that builds this mesh structure that you can see here, that's optimized for fabrication. You've seen the red parts before in this animation. Red is when fabrication cannot work anymore. So it's optimized for fabrication and for structural performance and for the spatial layout. And then this mesh structure can be filled with a manual process. So not everything is digital. It's a combination of human craftsmanship and digital craftsmanship. It's not advancing anymore. Oh no, okay, here we go. Good, so that's the builder, or one of the builders. Somehow it's not. Here you see it gets packed, gets transported on the building site. And now this is not a factory back area or a testing ramp. It's a real construction site, like you could find it anywhere in Switzerland, and I believe it's the first time that you have a robot on a real construction site like this. The robot is driven directly out of the CAD environment. So basically, the tool that we design this wall with is also the tool that we built this wall with. That's also quite a change in the logic. And this is a small documentation on how this wall got built. And sorry, if you take a look at the number of people and the robot on the construction site, you don't need to be worried in the short term. So we have about 4 people and 1 robot ratio. Good. Now this video got stuck somehow. Good. So here are, at least from our group, the proud finishers. This has been a work in collaboration with another roboticist called Jonas Buchli, who actually developed the entire robotic system. His people are unfortunately missing on the picture. But I think you also see that it's even a pity to fill this structure actually with concrete. It's so beautiful just as this doubly curved mesh in space. And you sense how the digital is very intimately connected to the physicality of this mesh. So here are some impressions. And currently it's being filled. This is the first layer, and there's going to be a top coat on it. And the remarkable thing here is that there is no formwork needed to build this wall. So there is no waste for any formwork. You can build a doubly curved wall, and so you save a lot of material, and you can structurally optimize the shape. You can also make differential wall thicknesses. So you can save a lot of concrete, and saving concrete is a big benefit for the planet, because concrete is the most polluting construction material that we currently have. It's most widely used all around the globe. Good. I quickly walk you up. This is another concrete technology which we have. It's called smart dynamic casting. It's basically a slip casting process where you can change the form during you're slipping concrete, and you can produce elements like these facade mullions. Here you see one in a kind of the drying situation. You see the final product, which have a very nice surface quality. We're almost at a kind of an industrial level. Again, you don't need any formwork to produce these forms. And each of these mullions can be different. So in this case, you have a different depth for each of these mullions, because the window panels don't have all the same size and don't have all the same loads on the windows. So you can have adaptive forms which have structural logics. Then this is a project of the professorship of Benjamin Dillenberger, and also our concrete, we call him concrete magician, Dr. Robert Flatt. This is a ceiling which is cast onto a 3D printed formwork. It's a very thin formwork, only about a centimeter thin, which has very intricate forms. You can see this almost naturalistic forms. You see this high degree of details, and you see how it adapts to the mesh mold wall below. So it directly takes over the formal characteristics of the mesh mold wall and reinterprets this with another technique. So 3D printing formwork, then casting a thin layer on top of it. Here you see an assembly sequence of how this is then pre-tensioned, of how these elements are then pre-tensioned. This is an early test which we did in the beginning of this year, and this picture shows how now these three different concrete technologies come together. And you can see they're all about beauty in some ways. They're all about material efficiency. How can we use less concrete? How we can reuse it wisely? How can we become very material efficient with building structures with concrete in the future? Now, on top of these three concreting strategies is a two-story timber unit. And this timber unit, what is special is that it's designed spatially, and it's also built spatially. So you see the design system. It's based on nodes. This is again algorithmically generated, and whenever we need to change some criteria change, we change the code, and then the system automatically adapts. This is the lab that we built it in. You've seen it before, the robotic fabrication laboratory. It's similar to the roof project, but what we do here is we cut these elements at a spatial angle, and we have two robots assembling this structure. So one is bringing material. Oops. You can see these complex movements in space, putting a first element in the corner, holding it there because it has actually a specific angle, so it's 90 degrees from one side, but it's slightly angled in the other direction. Brings a second element and a third element until you have a stable corner. Now both robots can let go of this structure, and you can start assembling second corner and so forth. You can then bridge between these elements. So you need to find a sequencing logic where multiple robots can actually directly build spatial structures, and you see then there is an expression of this building typology in the structure. You see how the robot, for example, once he places this beam, rotates in these side beams. So it comes here, drives in, then just rotates it in place. And you can sense that, yes, it's close to what the humans could do, but humans would really need to measure, etc. So that's why they like to build on a plane. They don't like to build in space. But the robots really have the accuracy to just put something in space, wait till the under comes, etc. This is also man-machine collaboration. The robots only really place the parts and cut the parts, and the humans do the connections because they're very fast, they're very agile, they see the details well. They can do minor corrections. So we don't need to automate everything to go into digital construction. A bit the complexity of these assemblies. Then we have a translucent facade developed for the system. This is roughly how it will look in the interior. So in the nighttime you will actually see the structure through the translucent facade. In the daytime it's actually very light, going to be a very light-filled spatial timber structure. Good. We recently launched a website, ifabhouse.ch, so if you want to follow, please go on the website. You will find updated information over the coming months. To finish, I would like to show one project, and to close the loop, I would like to take a topic which is dear to my heart. That's basically ecology, and exemplify this with this project. Rockprint is about the question, can we really build just with abundant materials, so materials that are available everywhere, in a way that we can fully reverse the process, so we do not deteriorate these materials, we just use them, temporarily bring them into a building, and then afterwards can bring them back to nature or build another building with it. It's difficult to do, but we have some first successes. So here we take just gravel material that you find almost everywhere on the planet, and we combine it with string. In this installation we build it in a box, but we have newer advancements where you can also do this without a box. Here a robot lays layer by layer a set of string, or this formation of strings, which you can see here. Then by hand we add a layer of gravel, and then another layer of string, and so forth. So now the robot embedded some information in this volume while building it up. And when we take the scaffold away, you sense there is some fall off, and if we then gently scrape this structure, you can unearth the information or the structure that was embedded by the robot in this gravel. So in the end you get this vertical structure, our rock print, which only consists of gravel and string. So there is no binder, there is no metal tube reinforcing this. It's just gravel. And if you walk on to it and you touch it, just gravel falls off. I did it a number of times with visitor there that said, no, that's not just gravel. I said, oh yeah, sure. And stuff falls off and they take a step back. It's quite scary. It's 2 tons of weight, and it's really quite impressive. So it stood for 3 months. It didn't move a single time. We monitored it, and then of course the fun is to build it back, because it's again not working, but this is another view. You can see the nice material expression. You also have these little rocks just sticking out. So it's really just material presence. And then building it back just means you pull out the string from the structure. So this now becomes a bit performative. And yeah, you see a close-up. done with it. So you end up with the same raw material that you had before, the gravel and the string, and that's it. So I just like to show this as a combination of technology, ecological ethics, which you possibly can bring together for a future ethics of architectural design and construction. Thank you very much for your attention.
Hello. Thank you, Matthias, for this incredible talk, which was 60 minutes sharp. I just want
thanks.
to.
I was worried by the watch.
No, you started at 6:17 and you ended at 7:17. I checked this. Welcome from my side. My name is Amelie Klein. I am from the Vitra Design Museum, and we opened a show on robots this February, which is why I'm here. And obviously we exhibited some of Matthias Kohler's projects. Very interested in I've been very interested in his work, in their work for quite a while. So what you've been saying a few times or alluding to during your talk, but also said in an interview once, is that you spoke about how robots turn the work of an architect into something more integral. Could you elaborate on this? What did you like talking about construction and planning?
Well, in principle, it reconnects architects with the execution phase of architecture. So in this case, or in many of the projects that you've been seeing, we're actually designing the construction of architecture while we design architecture. And I think good architecture is actually always thought like this. So, I mean, I would say there is a tradition in architecture to think about construction very deeply. And good architects also engage with the builders that they build with. But here there is a change of this link, because you explicitly start to actually design the codes that will ultimately be executed using robots. And so you very intimately connect to execution through that. And that's a new link, and it changes how classically architecture is separated into design phases and then execution phases. It starts to blur these boundaries and question the modes of how the profession of design and how, well, designing our built environment is currently organized.
So traditionally, or currently, what we see is the planning phase is executed with computers and software and robots potentially, but then once we start construction, we go manual, if you want. And so what you're suggesting is that in the future, potentially, the architect is connected to the process of construction in a closer way. Now, the elephant in the room always when we talk about robots, of course, is the loss of jobs. This is something that's always in our minds when we talk about robots. So the architect gets more, if you want, work with the construction, being closer to construction. But how about the builders? How about the foreman? Will they lose their jobs?
Very poignant question. No, I don't think so. I mean, I think what's very important, I mean, equally important probably for the architects as well as for the construction companies, is that they get into this digital culture and say, okay, let's open up and see how our practice of building can actually be informed by the digital. It's also important for the youth on construction sites. There's not so many people that are so eager to really get the construction jobs that are currently offered. You know, I think bringing the digital technologies to the construction side is also opening the construction to many young people that are inherently connected by the, you know, their mobile phones, etc., to the digital world. And so ideally, if you think a bit about future generations, there's not so much of a gap. Of course, there is societal problems, like with every change of technology that happened, particularly with existing, you know, generations of workmanship, people that don't want to change, which I can understand that this might cause some problems. It's not going to be easy to resolve. I think, though, because construction is not the fastest industry on the planet, I trust that we will have some decades time to actually adapt to this transformation and find good solution. And there it's very important that there is an ethical stance on behalf of all the involved parties in this process. So I would hope actually that the craftsmanship of yesterday and possibly today actually transforms into something like a digital craftsman in the future, and just speaks the same language like an architect who's also working with certain algorithmic tools. Then the interface becomes very easy, and you can actually collaborate on the same digital model or on the algorithms that create it easy. Actually much easier than just handing over a plan, which is then possibly misinterpreted by the one receiving the plan.
Also, I think we have a very romantic vision and image of craftsmanship, right? We think of the carpenter really working with, you know, these old tools. This is not the case anymore anyway. So
today's construction can be pretty rough. I think it's not the crafts, it's not arts and craft most of the time what I see on the construction side. So I think that's why I think there could also be something to gain, and I think the real, let's say the real craftsmen that really just work with manual sensibilities, I think they will always continue working, because I think the robots, they have different capacities than the humans, and human intelligence and interactivity, etc., will always prevail. It's just there will be shifts and renegotiations, who does what, and possibly also new classical craftsmanship, because you reorient, you see what are the robots doing, what can I do, what the robots can't do, etc.
Now, what I'm really interested in is, I believe, a real paradigm shift. If you look at design in general, the designer is in control, like from the idea to the very final product, whatever it is, a building, an object. What we see, of course, in negotiation with, you know, production of building and the material and the budget, etc. But ultimately, the designer is in control from the very first idea to the very last execution. Now, when you have algorithms, when you have robots, there is a moment you do, as an architect, you do set the parameters, of course, as you said many times, but there is a moment of loss of control where you let go, because ultimately you define the parameters, but you don't define the way the robot then solves the problem at free will, quote unquote, of course. I think this is really interesting. Do you agree? Is there such a shift? What does that mean for architecture? Like the Zunft, what do you say? How do you say that in English? I don't know.
The professional legacy of
architecture.
Well, I would actually argue that it's the contrary. I think it's actually a gain of control in certain sense, especially with the reach to execution, which is very interesting. But there is this aspect that you're mentioning. I mean, let's say there's multiple answers to this, but there is a moment which I find very delicate but also very interesting, that you're actually discovering something. So when you classically design something in your sketchbook, you have a very direct interrelation of what your hand does, what your mind thinks, and how this is represented, and you start to get into dialogue with this. If you program architecture, you imagine something, you're coding it, and at one point you think, okay, this could do what I thought it might do, and you execute it. And then the machine does something which you said what it should do, but there is a moment of distance between what you said it should do and what it then does. And now you could look at this as a loss of control. I understand this point of view, but actually it's one of the most amazing things which you can have as an architect, because you're actually discovering something. It's like a kind of a dialogue with something slightly foreign. You're still controlling it, but it gives you something back, and you can be surprised by certain results, and then you change, etc. You slowly adapt what it gives back to you. And so in that sense, I would say it's not a loss of control, it's quite a bit of control. There is an excitement in this, which I think many of the younger colleagues that I sense that for example, the participants in the workshop here, they actually have. They like to play with the capabilities of algorithms. And so I don't see it as a threat. It's just a different kind of attention and different way of maybe sketching, not fully replacing sketching, but it's a different mode of production. So I'm not so worried there. Of course, you could say now, if you allude to artificial intelligence or all the I don't know, the more critical thoughts, you could say, well, if these algorithms that you interact with as a designer, if that's just a black box, if you don't know what it's doing, if you can't change it, then you might be quite removed, right? You push some button in some software, it does something, it gives you something, maybe you like it, maybe you don't, but you get this kind of a bit disconnected user. That's not what I'm talking about. I'm talking really about the computational designer that is able to some degree craft his own the results that he wants to ultimately design with.
So we don't want Apple to enter this business. Sorry.
I wouldn't be company specific.
You do enjoy uncertainty, though. You do enjoy unpredictability, I would claim, because you use clay, which, in and by itself, by definition, is very unpredictable. I mean, ask any potter, and he will tell you that clay is a really difficult material to get, to get in control of. So what is it that fascinates you about this unpredictability? I find this really fascinating, because I still claim that this is a paradigm shift. This is something that is a new generation of design architecture, a new generation of architects that embrace this happily.
I think it has to do with the shift towards this algorithmic design, which we've been discussing, in the sense that now you're designing processes, you're designing behavior, so you're telling the machine what to do, when, which input to read, how to react, etc., with a purpose, with an architectural intention. Now, if you have this capability, you can work on architectural geometry, which is something which has a lot of potential in architecture and is also currently used very widely in architecture, also in offices, etc. So you can script geometries that are very complicated and intricate and very difficult to produce or control otherwise, because it's too many details or too many variants of it. Now, to work with clay is using this in a different sense. So you basically go out of the descriptive geometry, which tells you basically exactly where everything goes, and you go out of the idea that you have materials which are fully, let's say, customized to fit in these geometries. Instead, you go out in the real world and say, well, that's also the real world, but out in kind of families of material, how they grow, how they aggregate when you put them together, or in the case of clay, how they aggregate when you shoot. And then you need to observe what happens when you, for example, shoot clay. And then you take this input back from a sensor, and you start to react on it. And this possibility you did not have in architecture unless you were a builder yourself. Then you could build something and you could say, okay, what do I do in this case? And oftentimes this is still done like this. Or you're the architect that literally stands on the building site, says, no, wait a second, stop here, or could you take this stone to do this and this? Now, in today's industry, this is very impractical, and architects becoming true builders, I think this is also kind of a very romantic idea, at least at the scale that architecture is operating today. So now it's very nice to create this intimacy through these robotic systems, where actually the robotic system can look at how something behaves, how material behaves, how you have self-formation, for example, the clay interlocking with another clay when it impacts, when it flies down, etc. And then say, okay, how do I want to design with that, and really work on these rules until you see it behave in a way that you think this makes sense for the architecture that you're designing. And then you're designing with the material process. So it's a very intimate process, despite the fact that there is a robot and sensor and an algorithm in between.
That's lovely. Intimacy. In general, you work with very traditional materials. I find this quite striking because, you know, robots, obviously, when we talk about robots, we talk about the future. When we talk about the future in architecture, we often talk about fibers, carbon fiber, glass fiber, whatever it is, you know, these new materials. Why are you so interested in these very traditional materials like a brick, wood, clay?
Partially probably because we're Swiss and quite pragmatic. So, I mean, nature has grown these materials, or we have ready-made processes which are available, which produce materials in certain sizes, certain formats, etc. It's an entire industry which is already there, and instead of changing the entire chain, which for some process would be needed, it's also nice to just look what can you work with today. What is already grown. I mean, you could also think of growing architecture, right, and controlling the growth of architecture. It just takes a bit of a long time, right? And so in that sense we say, well, okay, what has already grown, what industries are already there, and how can you now transform this with little steps into this digital age, and how can you then really connect directly to the construction industry today and demonstrate this at the full building scale. So with this I'm not excluding other materials, and we also did experiments with carbon fiber, for example, etc. But to solve two problems at the same time, so make this connection between, you know, these digital processes and architecture, and at the same time do in-depth material research is very tough. We already have robotics in our hand, and each time you start the material research, it has a tendency to go very deep. So you need to really think if you want to dedicate into that research. And yeah, possibly in the future we'll also look at other materials, but I think right now we really just like the natural materials available and the current existing processes. So
I also remember when we met for the very first time, quite a while ago, I did ask you about bricks, and you told me about this brick manufacturer in Switzerland who approached you. Could you tell that story, that anecdote? I thought it was quite interesting.
What was it about?
You basically saved this guy in a way, and took him further in his understanding of his own material.
Well, I would say that we saved this guy. I think that's I think he, I think he's taking responsibility for his own action very well. But in the sense, what was interesting is that he did a study as his final thesis project in an MBA study on the future of brick construction, and he was actually looking if it was worth to automate brick construction. And his study concluded it's economically it's not worth doing it. So he, for his business, and this is a multiple generation family business doing bricks in Switzerland, he took the conclusion, no, it's not worth to go into automation. And then he met us, and we just asked him, could you borrow us some bricks? He said, I don't believe in it, but yes, take some bricks. And then a long collaboration started for many years, and now he has two robots. He builds brick facades in different places of the world. Just I think produced a small piece for the Saadit office, etc. So it is interesting. The curiosity was there with him, but I think what he did not see at the first moment given is, it's not just an economic calculation, it's a new product which comes. So it's you cannot just say you save money with robots. Maybe you can, but it's actually, you need to look for a paradigm shift in your production, for new products which arise from these new technologies. Is this what you were alluding to? Or?
You were saying.
Okay, good.
I'm finishing up. One last question. So I would like to quote a professor for biomimetics at Schumacher College in the UK, Julian Vincent, and he says, in biology, material is expensive, but shape is cheap. As of today, the opposite was true in the case of technology. In other words, traditionally we used to build as if material was cheap, which even if it's not, like non-renewable materials. And shape is expensive. Now, with robots and robotics in construction, this changes dramatically. What does that mean for the future of architecture in terms of economy and ecology in material, in the use of material, but also in terms of the visual language?
Well, in order to answer short, yes, shape is cheap, which is really a big change to architecture. Sorry. Yes, shape is cheap, and I think the visual language of architecture might change quite dramatically through this, to some aspects. In some respects, maybe to the worse, in the sense that if shape becomes free, what do you do with it could also lead to many very arbitrary design outcomes. But if a good design culture establishes and a good dialogue about these new design cultures, then I think we can also look into very surprising and new aesthetics, for example expressing materials in their behavior.
Do you want to open up? No. Do you want to open up for the?
And it's been wonderful to have both of you here. But so many things push us to complete this wonderful dialogue. Thank you. No, gracias a todos vosotros. Thank you also.
Thank you, everyone.
And discussing your 1 hour sharp intervention, but sadly we have to continue, and the seminar goes on. Let me only thank to all of you, and of course to the Rollins Institute that has so generously supported this robotics seminar. So the seminar continues in the foundation headquarters, and the public reunion that we have had ends here. So thank you all. Thank you, Norman. Thank you, the Rollins Institute, and thank you, Matthias and Amelie. Thank you.